That's like my favorite amplifier.
This should be it. Okay.
Wait, but actually, Nick, can you share the problem for 1 minute? Just
Sure.
so people
Does this
can-
mean like the S is on the right side of the, whenever it like shoots up to infinity, the sound? Like whenever the sound's like reverberating like that, like does that mean that on the J omega axis?
Oh, you know where we actually had to done this review in the HKN teams because people were like, oh, we can, no, it's
Fuck it. Okay, well that'll be cut.
We're almost there, guys. Hang in there.
Okay.
Okay, I have these.
Yep.
Oh, wait, can you send me that on Discord? Just a snip.
Yep.
Thanks,
Exactly.
there you go. Wait, is our Discord chat?
I don't know. I think it's
dangerous?
safe. I think it's safe.
Well, look at it before you.
I'm worried about my other Discord chats.
So you paid for Notably, but then you paid for the extra add-ins?
No, I don't think so.
Recognize that.
Okay.
And
Oh,
did you give
never
it to
mind.
me?
Amiga, here you go. Yeah. Okay.
Wow.
Oh, explain what we're saying.
Explain what we're saying. Wait, I can paste it here though.
Thank you.
Wait, where can I paste here?
Oh.
Wait.
Folks.
There we go. Okay, that took a while.
I'm sorry. How's this to be done?
Can you see the problem?
Yeah.
All right, I'll give you a second to write it down.
Don't worry. You have plenty of time.
Oh yeah, you can be smart like this.
Oh, sorry.
Who's sharing the screen?
No one's here.
Okay, how we doing, team?
So
We're just writing down the problem.
That's great.
Okay, perfect. So now that we know what the problem is, the first question I'm gonna ask you, because I know Dr. Twatch asks you this all the time, which wave is a wave propagating in?
Positive X,
How you know that?
because it's a negative X, or negative 2 pi X, so therefore,
It's going
the
in
B is
positive
negative,
direction.
therefore it's moving in the positive direction. And since it's the letter X, that means that it's moving in the X direction.
Very smart, David. Good job.
What's a good way to remember it if you just lose your mind one day?
If you have a BX, take the negative and then take the variable, the X. If it's negative B, what do you mean the best way? Like,
Well, I could argue that there would be a minus omega W, and your statement would not
So
change.
if omega T and BX have the same signs, then that means that it's moving in the positive. No, it's moving in the negative direction. But if omega t and bx have opposite signs, then that means it's moving in the positive direction.
That's correct. Opposite signs, positive direction. Oh. Sorry.
Hey, we're just getting started.
Yep.
Is it being recorded?
It is, yeah. I'm just going to write on your tablet.
You can.
Okay.
I got you. It's so smooth. I don't know why the whiteboard doesn't work very well.
Okay, that's a great question. Do you want me to help you, or do you want it to be your problem?
No, please help me.
Okay.
It's not here.
Okay. So is there anything on the screen right now that just confuses you right from the very beginning? Do you not understand a word that's written up there? Or is it too hard to read? Is like there an issue? Okay.
It is fine for now, at least from back here.
Okay, that's good. That's good to know. Okay.
Anybody knows the relationship between electric field, magnetic field?
Magnetic field strength.
Isn't these old, what's his name, Maxwell's?
Yes.
We know how they're related? How magnetic field and electric field are related. So H and E. E of the electric field.
E is electric field, that is correct.
Is this a question or a statement?
It's a question.
Okay.
How are they related? Anybody remembers?
Is there a formula or a
H
statement?
of xt is equal to 1 over ln n.
Long end. New.
The intrinsic
Eta.
impedance.
Eta, that's what it is. Eta. Eta kappa nu. Duh.
Perfect. Everybody's doing great. This is actually a fairly easy question. I think you had a lot of homework on this.
Oh yeah,
Yeah.
every
Right
question
now.
is like a lot.
Okay,
It's
okay.
like
So
eight
I'm
marks.
think if he puts this question on the test, you'll be fine. This is he put it in our final. Everybody did pretty well.
Mm-hmm.
Okay, so you told me that the relationship between these is what?
Don't forget the name of something.
I wonder if they're gonna hear this.
They will. So besides this formula she's writing down, is there another way that you could solve for the magnetic field with relation to the electric field?
You mean like a way where we convert phasor and then convert back? Or-
Well, yeah, without even using the characteristic. No, is that the characteristic impedance or the
Intrinsic.
intrinsic impedance? Intrinsic impedance.
Maxwell's equation.
You know, the cross product. Yeah. Exactly.
And what is the first thing Twatch is gonna make you do when he gives you a time bearing, what is it called? Expression?
Convert phasors.
Okay, and how do we do that? Anybody knows what the phasor of the electric field is gonna look like?
Well, it's cosine, so.
And it's a function of what?
X.
Yes.
Mhm.
What do we lose when we go from time bearing to phasor?
Omega t.
Yeah, we lose the time, right?
Correct. Yep.
So we're just a function of position now. So who can tell me what the phasor is gonna look like?
Would be y hat e to the j negative 2 pi x plus pi over 2.
Mhm.
Well, good job. All right, that's one term.
minus z hat e and then copy the rest.
What is the rest?
The e to the power of j parentheses negative 2 pi x plus pi over 2.
For the z? All right, because we had, this is our z component, right?
Oh, I didn't see it. It didn't have pi next to it. Okay, then it's just negative 2 pi x.
Yep. Does anybody have a question of why? Okay, so all you're experts in phasors now. It helped.
That's
The first
great.
test really made you experts.
All the quizzes they've asked.
Yeah, all the phasor quizzes. Okay, good.
So are we done with part A?
No.
Okay.
And what is, so in this expression that I wrote here, what is k?
K is propagation constant.
Mm-hmm.
Yep.
And what is equal to in this case? We mentioned it earlier.
Kxk.
What?
Kx hat k.
Yeah. It's just x, right?
Yeah, it's just your x hat, it's your k constant. I'm so sorry.
And what's our other unknown? I mean, it's technically not an unknown, but anybody has a value for eta? Is that what it's called?
Eta. Yeah.
Eta? Did you program it in your calculators already?
Isn't it 125?
Yep.
for
Yep.
Intrinsic.
Yep. That's the best approximation.
Okay, do we have everything we need?
Yes.
Can we find h now?
If you want to.
All right, if we have the will to continue, okay.
If there's a will, there's a way.
Exactly.
Make sure that's the cross product, not the dot
Shoot, I no wonder I put these giants. I'm like, what is that? Wait.
How dare you not correct us? Wow, the cross product there.
Hold on. How do I make these obvious?
In rojo.
No. Oh yeah.
I forgot, are there different types of linear polarization states? No.
At different angles. 45 degrees, any angle really. Just goes back and forth.
I hope your cross product skills are better than mine.
50-50.
I found out a pretty easy way to do the cross products is what I've been doing is so k is in the x direction.
Yep.
So I would do x, y, z, 1, 0, 0, 0, and then
Exactly.
ey, and then negative ez, and then just normal blocking out both sides.
Exactly. Since it's a linear operation, all you got to do is just multiply or cross product your x hat to the y hat and the z hat, and you get a nice, very simple.
Yeah, you can always do right hand rule.
Correct. Is necessary.
I always get that mess.
That's not too bad at all. Right hand rule.
So if this is your x, your y, and your z, x cross y, it's z. It's going in that direction, right? Or
Correct. Yep. Right-handed. X, Y. And
which
Z.
one? Okay. So so x cross y That is C, right?
X cross Y, it has to be Z.
Okay, anybody has a question about that? How to do cross product? With your right hand rule, show me your hand.
Yep, show us your gang signs.
Which one's your X, which one's your Y?
Which one's X, which one's Y?
X is probably going this way, Y is going that way.
X, Y, yeah. Z is Z is your thumb. The
Z
normal.
is your thumb. X is your index.
Yep. X, Y, and then Z. Okay, now we can do it for the negative. We can do it for the minus C. We can do it for the minus C, right? So we do X, we do minus Z, and then what do we get?
Didn't you just make your middle finger a Z? Isn't thumb Z?
Wait.
Sorry, you do
Wait.
you do the X in this direction, then you go in the minus Z.
You're trying to do minus C cross X? Hold on. Yeah, minus C cross X.
Man, I
Wait. Here. This is minus C, this is X, this is negative Y.
Mm.
Because your positive Y would have gone, yeah. Anybody ever, but is that the answer? What is it?
It's minus Y.
I was doing, no, it's minus
It's
Y.
positive Y. That's right.
It's minus Y.
It's positive Y because
It's positive Y and positive.
yeah.
Oh,
exactly.
it's positive Y.
Yeah, we should look at yours. That's where you're
Oh,
wrong.
yeah, mine's wrong. Look at yours.
And so it was right. So yeah, this is your X, this is your minus C, then it has to be Y.
So thumb is Y?
Thumb, well, no. So the cross, all this is this thing, this is your A cross B, this is your A, this is your B, and then now your thumb is always normal to wherever these guys are. So if you have an X, a minus Z, then your Y is always normal to these guys, or your B, or your resulting vector is always normal to these guys. So if I had done X cross Z, then it would have been minus Y.
Okay.
Sorry, your paper was wrong. I was looking at it, I was like, what?
All right, we know the directions. Okay, now give me my paper because the number is the same though.
Yep.
Yeah, that's just that.
All we're going to do right now is just, compute the cross product and then write everything down. Are there any questions?
What was the requirements for the third problem? Like, could you just scroll up to that one?
The third problem, I can tell you right now.
Or not third problem, but like third section.
The third section, it was determine the direction of propagation, wavelength, and frequency of the plane wave.
Oh, cool. Okay.
So extra.
I didn't know if Twatch would get mad if I put omega t. He won't get mad if you put omega t. That I'm for sure. You don't have to write. You don't have to find omega t.
You found it?
Yeah, it's not hard. You need to at some point.
Yeah.
Okay, so that's clear? You feel great about cross product now?
Oh yeah, I'm looking on
Okay.
power density now.
Okay, so, but he wants a time bearing. What do we have here?
Phaser.
Time harmonic.
Right, so we have phaser. We're trying to go to, oh, and then, so it would be again a function of time and position. So we're still going in the z hat direction. You can leave your 1 over n, and then you all are experts now
Sure.
on how to go from.
Why isn't y negative? And the direction in the y. Why isn't it negative?
Because
The cross.
whenever you do the cross product, so that's going to be
Okay, let me
positive
see.
cross
No,
here,
hold on.
It's
and then it's going to go
X,
to
so
y.
X
so
cross
times
negative,
cross
hold
here.
on.
Or
I'm going to
negative
show
y
X
times
cross
here.
Z.
Easy. It
X
starts
cross-
out
X
negative.
cross y is z. Z cross x is y.
Okay.
So X cross C, would that mean
How do you
negative y?
move the negative over the blue?
Cover y, you get this, it's positive.
But since this is minus C,
0 times 0.
Right, I want to do it with my
Yeah,
hand.
but you can move this.
okay, so
Negative C is in this direction.
this is, so we can agree this is X, Y, and Z.
Right.
Yeah.
Okay, but then I can also say that this is then, I will show you another way. I can then say that this
No.
is, I can then say that this is X, Y, and minus C.
Yes.
So it'd be Y cross X is minus C.
Mm-hmm.
X cross Y is Z.
Mm-hmm.
Okay, so I've just changed the order,
Right.
but I got a minus sign on Y though. Okay,
Okay.
now I do Y. Oh, sorry, I'll do
No, that's
X
pretty much what I did.
cross minus
was-
Z.
I
Yeah, you did it
but-
exactly.
Yeah.
Mm-hmm.
My thumb points in.
Is this the Y direction?
No, no, no. This is not a direction. This is your vector pointing.
Okay.
This is X. This is minus Z, which is down, because we already defined that Z
Oh
is
yeah,
up.
X cross C, yeah, yeah.
So it'd be like that, and then your
X cross C, and this is negative Y.
no.
No? Hold on, so let's go.
Let's
You'll
just
teach me
continue.
later.
I'll
You'll teach me
continue
later.
That is a recording, you know?
It is.
Sorry, guys. Sorry for all of those of you who are watching at home later. I'm sure you know what cross product is. Okay.
Oh, we don't need a section about cross product.
I'm just gonna write the cross products up here. X cross X, X cross Y, and Y cross X.
No, I wasn't confused about the negative J. I forgot that in the Z direction was negative.
Oh,
That was it.
Yeah, that makes sense.
I had it as positive.
Okay, anybody wants to tell me what the first the first time bearing is gonna look like?
It's gonna look like, y hat 1 over 120 pi
Mm-hmm.
cosine of omega t minus 2 pi x.
Yep.
And then it's gonna be plus z hat, 1 over 120 pi cosine of omega t minus 2 pi x plus pi over 2. And you can convert it to sine if you wanted to.
No reason.
Okay, that was easy, right?
So first was good?
Okay, this is answer A. So you've got about 10 points.
25.
Oh, 25 now, because it's,
It's 25 for part A.
oh shoot, wow,
Such a simple answer though, right?
lucky you.
Alright, glad to get
Easy
25
answer
points
if
on
you
this
know
one.
how to do cross product. It's not
Yep.
your strength.
Exactly, your minus signs are off.
Okay, now part B is determine the polarization state of the plane wave. That's my favorite part.
Mm-hmm. Do you guys feel comfortable with polarization state?
No.
Wouldn't mind another.
It's easy enough to be real high.
Oh, but do you look at the E or the
I
at
look
the
at
E? Okay, so this I could have got. I got it right.
Mhm. The units?
Oh yeah, yeah. Did I forget the units?
What does it originally state? Volts per meter, so then it would be amps per meter.
Y equals Z0 to Y.
Amps per meter.
I think. Okay.
I don't know
Oh, I
what the
didn't.
units
To watch
are.
it didn't count me off.
Well, what's it called? If E was in volts per meter, this is amps per meter.
It is in volts per meter, so it
Yeah,
would
that's
be an amps per
definitely
meter.
amps per meter.
Maybe I got the benefit of Tawashi not coming down so hard.
Oh shit. Okay. Okay. All right, so part B. So when we're looking at polarization, we look at our electric field. Oh, can you put it in the team screen? And we look at it in the time-varying form, right?
That's how we'll look at it, yeah.
So pretend you have and then This question is for you. Because the wave is traveling in the x direction, we don't care about it, right? Because that
Well,
doesn't have
well-
to do with the...
Well, what we want to do is we want to stand in front of the wave so that it's coming towards us. And so since we know it's moving in the positive x direction, we then have to define our right-handed coordinate system so that we get the correct coordinates on this plot right here. So if x is coming at us, right, that'll be your resulting vector, what gives you a positive x. Y cross z.
Okay, does everybody, x is coming at us, right?
Yeah.
Everybody understands this notation. If it's a dot, is the arrow coming out of the page, and if it's a cross, is the arrow going into the page.
Yeah.
Right?
Mm-hmm.
So x is coming towards us, and we have our positive y and our positive c hat marked down here. And so what we're trying to figure out is in which wave if it's moving in the left-hand circular or right-hand circular.
Or
right?
linear or elliptical. Good luck with that.
So these will be LHC or, well, I'll leave these here just for a sec, and then these will be RHC.
Yep.
Okay, so now we need to figure out which direction it's actually moving. And what I found a great way to do this is just look at how the wave is varying with time and plot two values, and those two values will tell you in which direction it's moving because you're advancing in time. So you'll be able to see if you're going this way or the other way.
Right hand or left hand. Yep.
So we remember this is our time varying. I couldn't mute my iPad. And so we're gonna let x equal 0 the whole time because we don't care which direction we're moving on the x, we only care which direction we're moving on the y or the z.
Exactly.
So we'll just write t equals 0 and then t
Exactly.
equals 1 maybe?
Yeah, we can do that, or we can make it easier.
Exactly.
So if we look at omega t, let me see what we're... So t equals 0, great decision. That's and then I let my other one be pi over 2 omega. What did you let yours be?
I let mine be pi over 2 omega so that we can get rid of the omega completely.
Yeah, you get rid of the omega term completely. And then other tricks happen. But you want something that will make your cosine and sine terms as easy as possible. You don't have to pick like 1.5 for random numbers.
Mm-hmm. Make it easier for yourself.
Okay, and do we agree that 0 is first in time than any other value, right? We're going from present to the future. Okay, so going into the future. Okay. So let's plug in our 0 and our t equals 0. So now my electric field at x equal to 0, comma t equal to 0.
That would be negative z hat.
Yeah, very smart. But for my slow people out there, we're gonna do the whole thing. Love you all. So my x term is gonna cancel here and here for the next of the problem because we don't have an x. And when t equal to 0, here and here, I ended up with this equation here.
Mm-hmm.
So we ended up absolutely right with 0 minus c hat. Right, so at my initial value, this is where I was. So let's go back to our sketch. And let's plug in our first point, which is at t equals 0. I'm here.
Awesome.
Any questions? loving this problem so far. You got more than 25 points in the bank. That's more than the average in any Twatcha test.
This problem is more than any average in the
Yeah.
Twatcha test. Maybe not for your class, but all those retakes. I'm just kidding. I'm so transparent. And so we'll just go ahead and plug in pi over 2 times 1 over omega into our equation that we had just previously defined before to get our next time states from our E field.
What is cosine of pi over 2? Fast.
Was it 1? Negative 1.
Pi over 2 cosine?
Cosine pi over 2. Oh, sorry, 1.
So
That's 1.
It's 0, right, guys?
Yep.
Okay, you can plug it in your calculator if you have trust
please,
issues.
please plug it in.
What is
Correct.
cosine of pi?
-1.
Excellent.
Excelente.
So we went from -z hat to -y hat. That's probably to the right.
So
That's
now-
to the right.
Now what you can do is you can use your left or right hand and curl your fingers in the direction that it's traveling. So if I were to curl my right hand, I want to make sure that my thumb's facing towards me, which is the direction of X. You want to make sure your thumb is in the direction of X, which is the propagation direction. And you want to see how your hands or your fingers curl. So obviously I can't curl with my right hand in the direction, so my left hand tells me, okay, X is coming at me, and I can curl with my left hand fingers, so therefore it's left hand circular polarization.
So if it curls to the right, it's a left-hand curl.
No, the
well,
other way.
that's technically going to the left right there.
Is it? It's.
I
No,
mean,
this is going to the right, but
But it's traveling to the left if you go from.
it is traveling to the left. Like
It-
if
it-
you go here.
It goes in a circle, so it'll obviously travel to the left and the right. It has a period, right? It's just a sine cosine. But you want to make sure that your thumb on your hands point in the direction of X, and you want to see which fingers curl in the direction that you've just drawn.
And whatever hand you're using is your polarization.
Exactly. Yep. So you just fill in whatever hand, and you fill in the circular.
Or you can just write these and remember it forever. Hold on. No, that one.
That's
say.
left. Yep. Awesome.
Then we're gonna make Christmas tree. Sorry if I'm being inappropriate for those of you who are
A star.
celebrating.
Still liberating.
Okay. Okay, so let's look at this question.
10 points.
Okay, so you are 35 points in. You're feeling great because you can actually answer a question in a Twatch exam.
Under direction of propagation, right?
Right?
Exactly. Yep. There you go.
So that's another 5 points. So you are 40 point, 25, 10, 35.
30.
Yeah. 40? Okay, we're still missing 10 more points, which is find the wavelength and the frequency. So let's finish part C.
Good luck, guys.
Thank you, Connor. See ya.
Thank you, Connor. So direction. No, this part.
Mhm. And frequency.
Anybody remembers how to find the wavelength?
That's from lambda equals 2 pi over beta.
I don't see a beta. Where's beta?
Oh, beta is the 2 pi.
Okay. Yep. It's K. Yep. Your wave number.
It's one of those. He's a good guy.
Hey, forever. So what's lambda?
1.
Yep.
Bien.
And what's your frequency?
3 times 10 to the 8th.
Why? What's
Because it's c over lambda c over lambda over square root of epsilon, or the relative dielectric. But since it's in free space, the relative dielectric is 1, therefore it's just c over lambda.
wait? Compute units.
Meters per second divided by meters.
Thank you.
Another great equation for finding your wavelength or K or whatever you may know is K, your wave number is equal to your radial frequency multiplied by the square root of your permittivity and your permeability of the medium.
Which one?
It's flipped. Yes, yep, there you go. Mu and epsilon. There you go. And since we know mu naught and epsilon naught because of free space, you have the square root of mu naught epsilon naught, which is just 1 over c. And so you have omega over c equals k.
How many different points of T did y'all use for determining polarization?
Just
It's
2.
2.
Just 2?
I did 3 just to make sure because you never know, but yeah, it's turned out to be right.
Yeah,
Because I mean, if you just do 2, then that would just be like, this is a straight line. So like, how did y'all determine?
no, it will tell you if you're going in this. If your first point is here and your first point is here, you're going this way, right?
Well, it is directly a straight line. It's not a you have to cross x at some point because this is a plane wave. You're not separated away from x, so you actually have to travel some distance around to get it. Because if you have this plane wave right here and it's somehow, I guess you could say almost rotating, right? It's not only oscillating between these 2 points right here, because they would have to be shifted away from your x. Your direction of propagation is not in the correct location.
What was the third point that you?
Oh, sorry, the minimum would have to be at your origin point. Sorry, that's why it would be different. That's why I wouldn't.
Because like, is that? Oh, that's T pi over omega. Okay. Yeah.
Yeah, that was my second point.
Okay. Yeah. Thank you.
Sorry, my third point.
Because I just know on this test I will not be able to reason in my head how things are supposed to be done. So I just gotta rely on the numbers.
Mm-hmm. The book was very confusing about this. We really didn't trust the book with what it was saying.
Do you want to send me the other problem in Discord?
Sure. Okay, so did anyone have any questions about that problem?
It's the easiest one ever, so make sure you don't screw it up, because that will get you very far.
Rub it in there, yeah.
Yes.
I screwed it up. That's what I'm telling you, don't be like me.
Alright, so we
I'll let them see this problem as well for a very
Yeah.
extremely long time. So this problem right here that we're about to do is a combination of some of your electrostatics, magnetostatics, all kind of wrapped into one. I don't know if does he discuss with you guys about quasi-static approximation or?
Yeah, he's talked a little bit.
Okay, so this is one of these problems. So I'll let you guys write it down. Hopefully you guys can see. Yeah.
50 points.
Yeah, 50 points. So our first problem on our exam was an impedance matching. That should be pretty simple if you have a program to do it. Shouldn't take too long.
Alright. This is a problem.
It is a problem.
Oh, it's not much fun. Good luck.
Oop, so sorry about that. So is there any hesitancy about starting this problem or questions that may arise from this problem?
So we have 50 turns in this. I'm assuming it's going in the Z direction, right? On top of one another.
Exactly, since this is a right hand a right hand orientation of a graph, then Z is obviously out of the page. So you know that your normal surface vector of your coil is in the Z direction. How do you angle this up?
It's kind of shitty, but just be brave.
Oh, okay.
I know, I need to buy it.
Just go ahead and write down these values. 10 ohms. We'll write C.
Oh, so I didn't see it there.
Mu equals mu naught. Sigma equals 2.2 siemens per liter. You know, A equals.
Can you see this one?
What was the very last part? The very last answer. I don't know if I forgot something like units or. Okay. So our first task is to find the self-inductance of the coil. Do you guys know about that? Self-inductance? You guys did a lab, right, where you had two coils, you had to find the mutual inductance.
Did you do that lab?
They did.
Okay.
Yeah. Not that we memorized the equation.
It was like lab 5-ish.
Yeah, lab 5, yeah, I remember that one. Oh, my goodness. So we had to find the self-inductance. So he told us that we could assume that the magnetic field is concentrated at the center of the loop. Not really, obviously there's some magnetic field here, but most of it can be concentrated right there. He wants us to find the time average power dissipated in the resistor, and then he also wants us to find the displacement current. So where would we find the displacement current in this circuit right here?
Capacitor.
Okay, that's correct.
Smart.
Yep,
Somebody took many capacitor problems on test 2.
exactly. Do we have displacement current? Do we know it exists?
Yes, because we have conductivity.
No. Displacement current is caused by change in voltage with respect to time. So because we have a changing voltage, we do have displacement current. If it was just constant current, or if it was constant voltage, then there would be conduction, but it would not be displacement. dV dt times C equals I dt.
I agree.
Okay, so let's start out with defining what self-inductance is. So we had to ask to watch him when we saw this problem when we were doing our own practice, and he gave us this formula, which you can find in the book. I wish I had the page written down. I didn't have it written down on my actual test, but
Trust me.
yeah, if you want me to, I can actually find it. So we know the self-inductance of a loop is defined as
They probably tried from their from their lab.
L equals N magnetic flux divided by I. And then
But they might find it like these. No?
that's N times I. They
Yeah, I
will
know,
find it by
but,
capital lambda.
yeah.
So this is also written as capital lambda over current. Okay, now
The entire equation, or so L is equal to.
No, the entire equation.
N
Okay.
I, or I, what is this, gamma, I think, I don't know, or phi, sorry, is equal to capital lambda. There you go, it's just the exact, just another way to write it out, another way to confuse students. So now what we need to find is, okay, well, we know N, we don't know I, but let's kind of leave that for later. Let's try to find our magnetic flux. And so what we'll do is we'll approach this by using a formula. This is the one I was talking about in the book. So our magnetic field, or our magnetic field strength, I believe, is defined as, where's the eraser? Up top, okay.
Oh, and you can double tap the pencil.
Oh, yep, exactly, yep. So our magnetic field at the center of our loop is defined as z hat, or it's, I think, defined as radial dis, or if you have, actually, no, it is defined as the z hat direction, mu naught times I over 2r, which is your radius. Okay, so now how do we get this in terms of our flux? Well, flux is just equal to the, I believe, open surface integral of b dot ds. If we want to, we can draw out our coil, try to figure out what our ds vector is. ds is basically just in the z direction. Since we have a coil, we have our x direction, we have our y direction, and so we have our z direction. Our dA vector is in the same direction as z, so b dot ds has to have some z component there. Okay, so now we'll just go through this integral mu naught I over 2r z hat dot z hat dA. Z hat, that's just 1, or dotted, of course. So then what we have is our area. Area of a circle, what is that?
Pi r squared.
Exactly. So now what we'll have is this formula, or this equation right here. This is given as mu naught I pi r squared over 2r. Okay. This guy right here, we can just now rewrite it. We can cancel out an r, so we have mu naught I pi r over 2. And this right here is equal to our flux. Okay, so now what we can do is we can go back to this, we can go back to this equation right here. Do you tap it on the top or the side?
The side. And then it shows on the top where
okay.
you are.
Thank you, okay. And so now we can go back up to this equation right here. We can plug in our flux, and luckily for us, we see that an I will cancel out, so thank goodness we don't need to find that just yet. So L equals our number of turns times mu naught I pi r over 2, and then we'll multiply by I on the bottom. So we'll cancel out an I, and then we'll be left with n mu naught pi r over 2. And so what you can do is you can plug every value you have in. So for n, I believe we have a 50 turn coil, so I'll just write it down. N equals 50. Mu naught equals, let's see here, 4 pi times 10 to the minus 7. There's probably some units, but who cares? And then our radius, our radius is 0.5. Okay. And then what you should arrive at for your self-inductance is equal to 49.348 times 10 to the minus 6 henries. Any questions? Okay, so now we found the self-inductance. That's great, 15 points. Didn't even have to do anything.
Microhenries, right?
Yeah, micro.
Cool.
It's straight up henries.
Well, you can put micro.
You could put micro henries.
I put micro henries.
Yeah, I just do 10 to the minus 6 is what shows up on my calculator. Don't do anything fancy. Exactly. So now we have to find the time average power, which means we need to know the voltage and current. So what we think back to is our homework problems where we've had to use Faraday's law of induction to get the EMF voltage, or excuse me, just EMF.
What is the equation for power?
E equals half of, wait, are we going by electric field or are we going by
Average
voltage?
power.
Voltage times current conjugate divided by 2,
You're missing a part?
square root 2.
The real part.
Yes.
Correct.
Because it's power, right? Because complex power is a combination of real power plus reactive power. But average power is just the real part of power, right? Because when you take power, you learn all about complex power.
You don't need to take
Is
power.
that,
Power is the best.
You don't need to take
Is
power.
the reactive power just
The
power
fake
being
power.
wasted?
It's fake power.
Fake power?
Fake power, no.
It's like the foam of the beer. It's like the air in the laid bag. It's fake.
So I've written down VR, but that's basically talking about the power and the resistor, which is asking for. So VR, we can just say is,
Wait, what is VR?
Voltage?
It's a variable.
okay, so
How you find?
how do I find it?
Take
I
a
have-
circuit one.
I have a series circuit. Let's just draw the circuit right here. I have a series circuit connected to some, let's call it a source. Excuse me, that's wrong.
Oh, that counts as a source?
What value are we given? Are we given the current?
10 ohms, whatever capacitance. Basically all it is that VR is just equal to the current, IR, you could just call it IR, just total times your resistance right there. Times
Yeah,
10
because you
ohms.
know Ohm's law, right?
Yeah.
That's all it is.
It was just V time equals IR.
But I mean, I'm so glad that I've drawn this circuit because now we'll use it for actually something.
My circuit looks different.
We don't know
Because I
our
have conduction.
currents, though.
That's conduction, I haven't drawn it yet.
Okay.
We don't know current exactly. So how do we find current? We need to go through and
Main
solve for
and
the
name.
voltage.
No, I'm kidding.
So let's solve for let's just find the EMF, right? EMF voltage right here. So we do VEMF, which we're just applying Faraday's law, is equal to N minus N with number of turns ddt of the flux, basically. So which is B dot ds.
Beautiful.
Exactly. So let us write down what B dot ds is. So this is obviously not the exact same B dot ds that we used before. It's not even close to what we used before. This is the actual magnetic flux, field intensity that exists in this area that we're at right now. So it's this guy right up here. So I'll write it back down here. So we have your magnetic field intensity, H, is equal to y hat minus 2z hat 10 to the 7 over 4 pi times some cosine term. Cosine of 2 pi times 60 times t.
Or you can just do 120 pi.
I know.
10 to the 7 divided by 4 pi, right?
Correct.
Okay.
Yep. Okay, so now I want to find out the relationship between B and H.
Any questions so far?
Just
I kind of missed the last part.
a part A? Sure. So where did you get a miss?
Right at the arc graph, you got the center.
Oh, for sure. Okay, so this part right up here?
Yeah.
Okay, so all that I was saying is self-inductance is defined as, so with L is your self-inductance, it's defined as the number of turns of your wire or your coil multiplied by the magnetic flux, which is capital Phi, and then you just divide it by the current in that wire. And this guy right here is just a simplification for N capital Phi, and it's just basically capital Lambda, whatever. All that we're looking for right now is our magnetic flux, which is this guy right here. And we just find that by calculating the magnetic flux strength in this guy right here. So B in this case was not found from using the H that's present in our medium. It's in fact just the B enclosed at the center of our loop.
And this is an equation in your textbook, right?
This is an equation.
That B is an equation.
This L is an equation. This I, it should be known what it is, magnetic flux. I believe it's also an equation. I mean, physics too as well brings back memories. Are you caught up?
Yeah.
Okay, if you have any questions, please just ask. No, this is the time to ask them. Okay, so like I said, I want to find the relationship between our magnetic field intensity to B, and the way I always remember it is B, so B mu H, B equals mu H. It's just a fun way to remember it. So this right here is our exact representation of that. I'll also write out here as well when we go to do DS, which is this guy right up
Can you
here.
put your vector hands?
Oh, I mean,
Yeah, you have to?
I don't put the vector hats. I do it when I do it in the thing because Twacha was very
He
crazy.
takes out points for hats.
Yeah, I
don't
put
think he
hats.
did.
I put hats all the way through.
But generally, this is a true statement right there because it could be
Sure, it could be
He took out
magnitude.
points on the last
it could be
one.
just magnitude exactly.
I
Yep.
think he's still a junior.
Okay, so now what we'll go ahead and find is our B in terms of our H. So we'll do B of T is equal to mu naught. Since we are not in any special medium, as it tells us it's in free space, air, basically, we can just do mu naught. This guy right here then turns out to be y hat minus 2 z hat over 10 to the z over 4 pi times our cosine term. Okay, luckily for us, mu naught and this term right here cancel out. So then we're just left with y hat minus 2z hat times our cosine term. Isn't this awesome? No special freaky numbers. Yet. Okay.
Everybody good so far there?
So now let's bring back down our equation that we were writing up here. We were trying to find B originally, and now we found B. ds, this is our surface normal vector, or the whatever normal vector to your surface. So this guy right here is straight up in the z hat direction, so ds equals z hat dA. We did that before as well, but now we're just doing it with this. So we'll have our, let's see here, I'll just write our flux, not to confuse, I don't want to confuse you guys, never mind. Okay, I'll write out the entire equation. So we have VEMF is equal to minus n d dt of our integral over a surface, doesn't matter, dAs, whatever. It'll be y hats minus 2z hats cosine of 120 pi t dot z hat dA.
Do you guys understand why it's in the positive z hat direction?
Okay.
What? Okay, show us why. Show us how you know. What tells you it's in the VEMF is in the positive z hat direction?
VM, yeah. B doesn't have a direction.
The what?
B doesn't.
Wait,
B,
are you asking why it's in the positive z direction?
yeah, why is your ds vector in there?
Yeah,
Isn't
you're.
it whenever you take the derivative of the cosine turns into the negative sign? So then you multiply the y hat and the z hat by negative? Or is that later on?
So let us imagine that we have a surface not in the xy plane, but we have a surface in the xz plane, which I will draw right here.
You're doing all three planes.
So that it'll tell them that not exactly, it doesn't always have to be the z hat direction. So I'm going to draw a coil in this direction right here,
Which plane is that?
the xz plane.
Okay.
It's normal to the xz plane. So now I'm going to draw a vector that's coming off this surface right here. So we can imagine this guy right here is just some circle in the xz plane. And it's normal vector, i.e. whenever we were to look at this at a flat plane. So now I will draw it as a flat plane. There's a circle right there. Well, I mean, we can obviously see right now that y is perpendicular to that surface.
Yes.
So our surface normal vector, which also comes up perpendicular to that surface, we'll just call this n hat. N hat and y hat, let's call it, are in the same direction. And so we know from our dot product that if they're in the same exact direction, the magnitude of their dot product is always 1. Okay? And so we can just call this normal vector the same as a y hat because it's in the exact same direction as y. There's no issue with that. And so this is with another plane. However, we are in the xy plane. And so our normal vector is exactly parallel to our z vector, or it's perpendicular to our
Right.
surface.
So you could change the z to a y? Yeah, you can just draw
Yep.
them.
And so now what I will do is I will just change this guy around right here. And I will just draw back in what our actual plane is looking like. We have an x, we have an y, and we have a z.
Okay, does that make sense why we're in the z direction?
No,
Yeah.
for what was the original circuit looking like?
That one that he just
The
showed.
left one?
No, the right.
The right one? Okay, so on the right one, like that has the
Yeah, your circle is in that plane with the X and Y.
with the resistor and capacitor
Right.
attached to that
Correct.
one.
Right,
Yep.
and so this is your problem, and here coming out of the page is your C hat, your positive C, that's why.
Yep.
So could you provide an example where n hat is going the opposite direction of z?
So that is also a good point as well too. However, we like to define our normal vector in the same or in the positive direction. So you do, since you have some surface, you do have both a positive vector and a negative vector, and of course your dot products are going to be opposite in magnitude. But we want to make sure that they have the same magnitude, so that's why we're sticking with the positive direction.
So I think the original question was how do we know if it's going to be in a positive z direction or a negative z direction? Right?
No, he won't ask you if it's in a positive or negative C direction, he'll just ask you which direction is going, the positive or negative was for the previous problem with it.
I'm asking because he was trying to ask us a question if we know something, and then he tried to explain it, but then I got lost in his explanation.
Well, it was not about if it was negative or positive, but like he showed the other example, it was if you were on another plane, you would be a Y direction, like Nick showed.
Are you talking about what Dr. Twatch just said today, or did you talk about
No, I'm talking about we were here,
this? Okay.
you were right here,
Yes.
and then you asked the question, y'all know why this is positive?
Z hat.
Yeah, like what is that? What is it in the Z
And
direction?
then I didn't understand any of it.
Okay, let's
I think-
I also believe as well too that we want to stick with just the right hand rule in this case. You could define maybe your current going around in the anti-clockwise direction, so that your normal vector is pointing up as well.
I think what I got from it was that if you thought of this as the XY plane, and you have that circle loop, and you have the resistor attached to the capacitor, in order to get the full magnetic effect, it's going to be coming through here, I guess. I guess that's due to the curl or something of the wire. If the current's going around here, then that means that it's going to wrap around here, which, wait.
That would still give it
No.
a negative direction then.
Yeah, that would be negative direction.
You made it worse, Dave.
Wait a minute. That
Do
means
you have
going
the
down.
textbook? Because I think there was a good image.
Have
Remember
the
when
same
Twacha was trying to
Does
show
it-
us?
Did it define
There's
a positive and
Why
negative?
don't you just delete the question?
Yeah, if you can define it as a negative, you can
I
I just
believe
wanted
our
to-
just notation is just assuming that our normal vectors are always in a positive direction.
Yeah.
I think that would make
Exactly.
the most sense.
If you want a good lecture series to watch about this, I would recommend Dr. Walter Lewin from MIT. He discusses, I think, in Faraday's law of induction, his discussion on, okay, you have some surface and you have your normal vector. Which one do you choose? Well, he says the positive direction is the best one to choose. These are the solutions that how we
Why
do
am
it.
I
I mean,
talking-
positive is always going up.
So
Unless said otherwise, we can assume that's coming.
we want
Doesn't
really do.
we want to assume the positive normal vector.
It's just convention.
Okay.
All we wanted to show you was that it could be in the positive Y or in the positive X, depending on which plane you are.
I could also say, I mean, not to confuse you guys even more, but I will.
No.
I could also say that the downward direction is also a positive normal vector. It doesn't really matter. It just, somehow these guys will always, just work out.
Wonderful.
whichever direction.
Just, but focus on
Whichever
the,
direction
I will
Twacha
say-
chooses will be
I'll
the
continue
correct.
with
I will say what you want to focus on is which plane you are, and whatever variable is missing on that plane, that's the direction of your Z. Of your VA.
There is a video up that we've worked a problem like this before, so if you want more
Yeah,
practice on
where
this type
is
of
it?
problem, it's on my YouTube channel. I don't know if I put it on the Discord yet, but I will make sure that's up there as well.
So
Oh,
it's
that's great.
Z hat times Y hat.
It's not times, it is
Look,
dot
here it
products.
is.
Oh, 1.
Y hat times Z hat is always 0.
Because the V induced that's why. You have,
Oh, Y
the
hat
V
times Z.
induced is in the wire, right? But the magnetic field, or this guy opposes it.
Mhm.
And that's why it's going out. But
Yes. So if your B is going in the opposite direction.
You can put this image in there if they want to.
Okay. I think it's okay. I'm going to continue on.
Okay.
Okay, so let's just perform the dot product. Dot product with anything but z itself is going to be 0. So we have y hat dot z 0. So screw it. We'll just forget about it, and we'll just do -2 cosine of 120 pi t dA. What does dA vary with? dA varies with respect to
Time. Or D.
dx dy, yeah, whatever. So we don't need to worry about this being in there at all. So we can just take that out, and we can say VEMF is equal to -50. I just replace the number of turns ddt of -2 times cosine of 120 pi t. And then now times our integral of dA, which is just area, super easy, -50. I'll get rid of the minus sign actually, since we have this -2 now out. So we'll have 100 times cosine, excuse me, ddt of our cosine 120 pi t times area, which is just pi r squared. Okay. Only one thing's varying with respect to time, so now we can take the time derivative of that. And what we get is the following.
Aren't we given our area already?
No, that is the capacitor's area.
Oh, okay.
Yep. So we're given the radius of our 50-turn coil. So we'll just do 100 pi times r squared times 120 pi times, okay, well, what's the derivative of cosine, guys?
Negative sign.
Smart.
Awesome. Let's see here. So now we'll have minus sign of our argument inside, pi t. So we can plug in our radius, which is just 0.5, square that, you get 1/4. And so we can just do 12,000 pi squared times 1/4 sine minus up here, sorry about that, minus up in the front times sine of 120 pi t. And so we'll get the following for our VEMF.
Wait, that's not pi squared, is it?
That should be pi squared.
Yeah, it's
Oh,
squared.
it's those pi's, yeah.
Yep. We'll now have minus 3,000 pi squared times sine of 120 pi t, which is our VEMF. But we're not done. Sorry, guys. Okay, so now we need to actually go back and consider our circuit. We've now confirmed that we have a changing voltage. So now that we have a changing voltage, we can then redraw our equivalent circuits as the following. So we have our original load resistor right here, so it's 10 ohms. I'll call this R conduction with the sigma notation. And then I'll just call this our capacitance, right? That's simply what it is. Now it is strictly a capacitor with no parallel or series resistance. The parallel resistance is already taken out. So capacitance is simply defined as epsilon times your area of the plates over D. Sorry, times the area of one plate times D over D. What you get from this, I'll write down our medium characteristics again. They're up here. 4 times epsilon naught, and then area is 0.01 meters squared. Meters squared. Okay, then we get our capacitance equal to 354.16 picofarads. There's your capacitance. Okay, so
What's the value again?
354.16 picofarads.
Okay.
You said 354.16?
Yes.
Awesome.
I'd be really concerned now, considering I'm looking at how small these numbers are, plugging this stuff into your calculator. if you have, please use your computer if you want to do something like this. The precision on MATLAB is much greater than the TI Inspire. So I think I do get this question wrong, but he doesn't say where I go wrong. I get the answer wrong, and I think it's really due to precision from my computer. So now we can calculate our conduction. So anyone know what this is? How you calculate the really resistance of any material?
I guess.
Or sorry, resistance of the capacitor.
J for
Yep.
that one.
Distance between the plates divided by your medium's conductivity times your area. Which makes sense, right? Because 1 over Siemens is ohms. So there you go. Now we will figure this out. This is 45.4545 milliohms. Okay. Now we just got to figure out what the total impedance of our load is. Simply put, we can just find ZL, which is just equal to our 10 ohms plus our R sigma in parallel with our XC, or impedance of the capacitor. I define XC as 1 over J omega C. Okay, and what we develop from that is ZL is equal to, I believe, 10.045, is that correct? Can't tell if that's a 6 on mine. I think it's 10.0455. Okay, so 5.858 minus 12 ohms. Is that what you mean? Yep, 10, okay. We're just making sure. I have very bad handwriting. Is that visible for everyone up there?
Where's your J on there?
Oh, of course, there's a J. There you go.
There you go.
Any questions? Yeah, I mean, calculation is kind of the slowdown.
I store all my variable. After doing this one, I store this one in my, it's the first variable.
This should,
Store in my
yeah,
calculator.
for sure store this. And so now what can we do? Well, we can find the current. Simply enough. Okay. And why do we want to find the current?
Because we're trying to find power.
Exactly. Don't lose sight of the problem, because you somehow you get so down into the meat of this problem that you just wonder, where the hell am I going?
I got everything up to very same as you.
That's great.
I
Okay.
don't think it was pointed.
No, for sure not. Okay, so VEMF divided by ZL gives you your I loop. Okay, and now what I'll do is I'll actually define them as phasors, because I prefer phasors, and also the equations and time average power is also in phasors. Okay, simply put, we can find VEMF to be equal to phasor notation, excuse me, of minus 3,000 pi squared times the exponential of minus j pi over 2. And why is that? Because we have sine right here. It's not cosine, so it wouldn't have a zero argument in our exponential form.
Oh, well, that's what we're different.
Oh my goodness, did we get that different for sure?
Because this is what I have.
You
So
might
I
have-
converted to cosine,
Yeah.
and then I had a I don't know if I could be wrong. I'll check when I get home.
Okay. I mean, I think someone would have, if you guys are experts at phasors, you should tell me I'm wrong, so.
Yeah. Magnitude would be almost.
I hope.
So sine is J, pi over 2.
What's your P average?
My P average is
43?
43.
Okay, so we're good there.
Well, it's also the real part as well, too, so 90 degrees, whatever, that's a minus J, doesn't matter. There we go.
Displacement current.
Why is this just pi over 2 right here?
Yes.
Minus J pi over 2?
Yeah, because it's going to be 120 pi.
We are in phasor notation, and it's sine. Our VMEF is defined in sine.
Yes.
So we have a, what is it? Sine of x is equal to cosine of x minus pi over 2, is that correct?
Yes.
And so this guy can just be written as e to the minus j pi over 2. Does that make sense? Okay. Any questions, guys, on up to here? Okay. So now that I've found our VMEF in terms of phasors, now I will determine our current through the loop. So I loop. We assume no resistance in the coil wire. What a great assumption. So now we will just do this. What are we going to divide by? Our load impedance. There you go. Since there's no current, since there's no resistance in the wires, we don't have to worry about that. If there was resistance in the wires, where would you add it?
Here. ZL plus Z wire.
You would do ZL plus Z wire. Yep.
Any questions? This is just Ohm's law. All we've done is Ohm's law. B equals IR, right? Wow, that's gross. I put it in face
Yep. That's how my calculator gave it to. Yeah, I always did. Yep. So now what I would have done is I would have stored my I loop. Okay. And how do we calculate time average power? I think we discussed this already. At the beginning, 1/2, your real part of, and we discussed it was just VR, which is just Ohm's law. We can just write it as I loop times your resistance times the conjugate of your loop current. So what do you get when you multiply your...
Wait, let me ask him a question. Why didn't we put BEMF there?
Why didn't we?
Yeah, let me ask.
Because, I mean, we already know how to solve for VMF using current and resistance. If we already found current, why don't you put it in terms of current?
No, that's
Okay.
not their answer. Any other volunteer? Go to the statement of the problem.
So let's not lose sight of what we're looking for. We're looking for time average power dissipated in the resistor.
Okay, so what is the voltage across the resistor? It's not BMF, right? Because we have the voltage drop across the capacitor and the resistance in parallel with the capacitor. So if we look at the circuit Nick drew,
Is this what? I can't remember.
that's the voltage. That's exactly the voltage across the capacitor, which is not BMF. It's just R times that current. Okay, makes sense.
We're
So,
finding the voltage across this guy right here.
yeah. So if you had put BMF, you would have been wrong because KVL.
Glad to hear it.
But if he asks you what is the total real power around the loop, then you would have done BMF.
Yep. So what we find is our power average, PAVGE or PAVG,
Across a resistor.
across the resistor, comma R, is equal to 43.4383 megawatts.
Yep.
Okay. That is simple, right? It kind of reminds you of your transmission lines. Pretty simple. Now,
Okay, that gives you how many points they are in?
so we've now gotten 40 points.
Okay, but was this way more harder than the first
Yes,
problem?
yeah.
Okay, so that's why you don't want to miss. I hope he gives you the other one.
All the time spent for this problem, right? Just doing the part B.
He said he'll give something like the first one.
Okay.
What was the current y'all got?
The current we obtained?
Yeah,
Did you get it in rectangular or face?
I'm in rectangular too.
Okay.
Great.
Do y'all need it?
Nope, there it is right there in rectangular.
I messed up something.
I mean, technically speaking, if we
Well, you
did
can watch the
this
video later too.
in this amount of time, then we would have to
So
end here.
we will continue on. Now it wants us to find the displacement current. And so let's go.
Wait, we did a bunch of problems in these capacitors. Anyway, what's the formula for displacement current? Go.
You can't just put on the spot like that.
You took a problem that had like 5 capacitors.
I don't think
I
they
mean,
had to
it's-
solve for displacement, did they?
No?
Is it partial D, partial T?
Yeah, just about.
Almost there, pretty good.
DDT.
DDT.
DVDT.
DDT times DDS.
DDS.
Look at these formula. What is your formula?
Oh, I would have done DVDT times C.
But look, our current is almost the same. What
Almost.
did you mean? Did I get 100 and maybe?
Oh, I think that right there. I had the wrong power of this guy. You have milliamps.
Okay.
I have microamps.
Okay, that might be the right answer.
Yeah.
'Cause that's
Oh, and also
important.
sign is different as well too. Oh, but you don't have anything inside of there, so I think you're wrong.
I'm wrong?
I don't know. Okay, so what we'll find is this guy right here is just I loop. We'll apply simple KCL rules right here.
I'm gonna ask Suzanne.
Yeah, if she has her test, that'd be awesome to know. IR and then IC. Okay, so we can define the simple equation I loop has to be equal to IR plus IC by KCL, our favorite, one of our favorite laws, one of the unsung heroes. Just goes unnoticed. Okay, and IC, let's redefine this not as IC but as ID so that we don't get confused at all. ID, we know ID is just displacement current. Okay, and if we want to solve for displacement current, we can just separate that to its own side. So we then have I loop minus, let's call this R sigma so we don't get confused. Sorry, I don't want to confuse you guys.
We're confused already, sir. Just kidding. We're not.
Indeed, that's great. Okay, now we have I loop, which we actually do know. We have ID and IR conduction, whatever, I conduction. We don't know those yet, so we have to find them, which means we have to find the voltage across this, I guess you could say, parallel impedance right here. So we got to find this guy. Well, funnily enough, we can figure out this guy just by using VEMF times I loop. Okay, simple as that. So we'll define this parallel voltage, which we'll call VP. And I call it parallel because it's just two parallel components, equal to VEMF minus VR. Okay, and now what I want to do is I want to define this as a phasor, just so I can get rid of all the time domain stuff. I don't want to think about cosine just yet. And so we know VMEF, we know VR. VR can just be found by I loop times 10. Done. Super easy. V parallel. I found to be 809.407 times 10 to the minus 9 plus 133.977 I volts. Okay. We now have our parallel voltage, so we can actually now apply Ohm's law and we get something useful. So V parallel divided by our conduction resistance gives us I conduction, or IR sigma, which we can then find to be 17.807. I think this is where I mess up. Plus 2.94748 E3.
Are you guys doing okay so far?
Could you explain again why VR was just I loop times 10?
VR, okay. So let's define this as VR. Does that make sense?
Yep.
So we have our I loop, which we know because we found that just dividing our total impedance of the load divided by VMF. And we can just simplify this down to circuits. It's honestly literally just as a circuits 1 analysis problem. So you have your resistance.
Oh wait, 10 ohms, that's why.
Exactly,
Okay.
yeah. Yeah, I guess I should have left the units here just so it wasn't arbitrary units there. Okay, we now have our I conduction, or IR sigma. Now what we can do is we know our I loop and we know our I conduction, so we can find I displacement. So we'll do I loop minus I r sigma, and that gives us I displacement, which is minus 17.88879, or 8,879, whatever, E minus 6, minus 32.5 E minus 9. And so I got this to be in actual polar form, and here's why. We want to go back to time domain, something useful for this problem. This way.
Slightly slow down,
Sure.
like.
Okay, so
0.99
I'll just leave it right here.
I asked Christian to show us what she got and then we can compare.
Okay. I know it.
Why my process is completely different? I did like the integral part, but the number seems similar.
Oh my gosh.
I know. But
KCL is so much better.
I mean, this is like 3 lines of work.
Yeah, but I mean, my process is founded in circuits. I guess. To each their own, right? There's so many ways to do everything. Is everyone caught up? I can still wait more. It's okay.
Give me like 2 seconds.
For sure. I'm trying to see if I wrote it down here. Where's the string?
What, the displacement current?
Yeah, displacement current. Did I not write it down?
Don't forget the J on the second part of the current.
There we go. We love I.
Oh.
Sorry, I do I or J's interchangeably. Being in a math class, you just kind of just
Disgusting.
have to live with it. Okay, and then now we'll just go on and rewrite this guy as phasor form so we can see it as something pretty easy to convert back to time domain. I don't know if you need to do this for this guy, but I did it because why not have more work to show?
One partial credit.
So this is our phase
0.01 partial credit.
phase angle right here. This is still equal to I d that guy right there. And now we want to bring this back into the time domain.
Of course.
So we have our phase offset and we have our magnitude. So ID of t is simply 17.8879 e minus 6 times the cosine of, okay, our omega t, which we left out for simplicity when we were doing everything, minus our phase offset, which is 3.1. Oh, you know why I got it wrong?
What?
I had an I inside. Okay, there you go. I think this is actually right.
Wow,
Yeah.
Suzanne has something completely different anyways.
Okay, there you go.
Well, at least we have the same. Oh yeah, Suzanne screwed this up big time.
Still got an 8 though.
Yeah.
Any questions?
Can you just go over that all over again?
Yeah.
Just to clarify, the entire problem or just this part?
Oh, no, that was a joke. I got it all written down.
Okay, I mean,
Actually, what was the power average that you found?
so the time average power was 43 megawatts. Mega.
Oh, cool. I got the same. Awesome.
Everyone going over 2 problems?
I can go over a third problem. It's completely different from all of these. It's pretty simple as well too. If you guys need to leave, this will be recorded as well. But I can go over this next problem as well. It's kind of chapter 8-ish. I don't know if you guys will see this, but
Go back to the end.
to the end,
Yeah.
this right here. Can you guys see that up there? No, my shitty handwriting. I hope this should make sense. Do you need to see more, or are you okay? Okay.
What one are you going to? The
We're
kind
not
of the curl, the math.
No, that's dangerous. This one.
There's the many or many. Use either.
What test was that on?
This was spring 20.
Oh, okay, what's that? Is that
Oh. Okay, thank you guys for coming. If you're leaving, this will be recorded, so the next problem, it might not be on your exam. I don't know if you guys have covered it yet, but please look over it if you can.
Which question?
It's similar. It's not an intended problem, of course. Thank you for coming.
Problem?
I think you need to go over the next problem, just in case.
Oh, no, I will. I just wanted to let everyone know what we're doing. Okay, so let me get this next problem up. Do you guys have any questions about the previous problems that you're thinking about right now?
Is it too late to drop?
Did you just convert the current to phasor?
Yes, so exactly. This entire time, I didn't care about the EJ omega t
Yeah.
because why? It's going to be somewhere in my form. It's going to be somewhere in my equations that I'm going to have to keep moving around. So I said, screw it, drop it, and we'll just continue without it.
So you stick the 125 out of it.
Exactly, because
And then brought it back.
it was never going to get lost anywhere, right? It was going to be there somewhere.
So you just want the rectangle for the entire time?
Exactly.
Oh yeah, this is fun. This will give them hope.
This will give them hope. So here's another problem that you can
This
that you.
problem is gonna take
It's like the first.
I can also show you a problem that will make you lose hope, but we won't do that one.
That's for next tutoring session.
If you want to see a problem that'll make you lose hope, it's underneath the projector screen
That's
right
called
now.
the one that's gonna be put on the test.
Okay.
Alright, kiddos, let's get into this one.
You're almost there. This one's not gonna take long at all.
Alright.
And this one is something Twacha likes to do, so I can see him putting it there, but
Okay, so it's two mediums, and it's propagating from one to the other.
Can I go into your photo
You might
library?
not have this problem then.
no, I don't know. No,
Well,
it's
you
sharing.
might-
Here, I'll show you how to do it.
I don't want, but I want to get the.
Electric fields last time.
Oh, yeah, we did. Not this.
Oh, shit. It's okay. I can't say that words.
It's okay. Just like Wes.
Hey guys, you have 2 viewers.
That's awesome. We gotta put this on TikTok.
Gotta get these numbers up.
How's chat doing? Chat's doing awesome.
Chat is a constant
Wait.
variable.
Yo, 5 bits. Thanks, man.
There we go.
Gracias.
You can charge me.
You can crop it.
So do I.
Are you getting an haircut now, Nick?
Silly. No.
Silly child.
Why are you not sharing the screen anymore?
I wasn't full, but I got this one.
Oh, wow. That is a great question. I didn't change anything.
I mean, I'm still in the call.
I shouldn't have even planted that seed in my bread. You know you slick. I can tell you something.
Are you using,
I guess you got that.
what's it called?
And make sure, I don't know, because did you hear yourself?
I do on this tab.
Yeah, I know, I
And
can't
like, you
remember.
can consider like a whole page.
It's okay, it's not too
Yeah.
And I created it, because I couldn't turn it out.
Awesome, we're back.
And if I did, like, it just looked long.
You can tell it's something there, but it's not like, only because you know.
Yeah, but it, like, it would have been like the letter page, so I had it.
You want me to write it?
Maybe just put
Or
I
you
can, I
good?
can write it.
Okay.
I'll be there.
Okay, so we ready for the next problem, guys?
Yeah, hopes are high?
Okay, so. It's
Make it a little
propagating
bit
in the
bigger.
Positive Y direction.
Make it
You
bigger?
can change like the.
So just
the
like
length of the
that,
page.
Yeah.
No, you can print it out, but like, because.
I actually-
it's continuous, it doesn't link itself to like another page.
So
That's what we shot.
I think this is a problem where we kind of design our own time-varying vector electric field.
What's so normal about it?
It's been going on.
Shut
So we have a wave propagating in the positive Y direction.
Oh, yeah, this was in the homework too. Yeah, so maybe this will be covered.
Nope.
This might be.
Where it's just going through. What's normal mean?
So this one is. just-
Normal means perpendicular.
What? Yeah, normal means perpendicular.
I think they had it.
Okay, and then we have a plane wave polarized in the X direction. We have a peak value of its electric field, and we have at the parameters it's located at. We have our medium characteristics for number 1, medium 1. Okay, so kind of a fun problem. We get to design our own incident field, time varying vector. So we'll just write this guy down, and I'll kind of leave basically this open for stuff to be filled in. So x, comma, y, comma, z, comma, t. Okay, so we have our amplitude times cosine of our omega t. And I guess now we should think about, okay, what direction are we in? So it says positive y direction. And we know from our argument inside of our cosine that the signs have to be different in order for it to be in a positive direction. So we now have just a minus. Let's see here. We can leave this as k. K.
Y hat.
Exactly. I don't think
Just y.
we don't need a y inside, a y hat inside. Yeah. Okay. And now this is where we have to leave room for our phase constant, which we don't know right now, because we will, but we won't find it just for a bit. So anything.
You were given the polarization.
You haven't solved this?
Yes, exactly. So the polarization, what does that mean? If it's in the x direction, where do we put that? We just put it outside, right? Times x hat. There you go. That's where our x hat goes. So now we can find our peak intensity. So peak intensity means what?
That's what it's equal to?
Sorry, that's a stupid question to ask. Peak intensity means what is maximum in our equation that I've written down here?
10 volts per minute.
That's the correct value that we need to go for, but what is at its maximum point?
Yeah, where would it go in our equation?
It'll go in the E.
The A value, right? That would be where our 10 is.
The amplitude.
Yeah, the amplitude.
Exactly. I guess what I'm
That's
trying to get at is how do I maximize this equation with a cosine in it?
Cosine's max at 0.
Exactly, right? It's max at 0 or whatever additional phase you have, like pi over 2 pi or whatever. Oh no, sorry, that'd be minus. So every 2 pi. So exactly. So now we just write this guy as cosine of omega times 0 because it tells us time 0 minus k times y.
This is the peak value.
Yeah, exactly.
Okay, to
Yeah,
0,
that's what I was
so
thinking.
that's just 0 again, so we have phase constant.
Exactly, and plus our phase constant. Okay, and then times x hat. And we know this equals 10.
Because in the homework, you'd have like 2 different values. One was like intensity and one was amplitude. So I saw intensity, I'm like, oh, okay, so that goes for the E, so that then you can solve for the theta.
Mm-hmm. So now we just have cosine of our phase constant times a in the x hat direction is equal to 10. Okay, and we want this to be a maximum. We know this is the minimum or the maximum potential ever reached, which means cosine has to be 1. Cosine's 1 when it's 0, 2 pi, minus 2 pi, whatever. And we want it to be the smallest. So we'll say the phase constant is defined as 0 equals plus 2 pi n, whatever, n equals 0 plus minus 1, comma, plus minus 2, dot, 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 whatever. You don't need to put that, but if you want.
Yeah, you do not need to be this extra. I don't know why he's being so extra, honestly.
It's an equation, so you have.
didn't even need
You
the
have,
phase.
you do have to define it for all points, so there you go. Now we have a equals 10.
Wait, so it was 10. I'm
Yes.
good.
Exactly.
My gosh. I know to rewrite everything. I was right the first time.
Well, you got to show work. Else, it did say underneath this problem, all work must be shown to receive
didn't
credit.
show
I'm not
it.
even kidding you. It really did. So. What'd you say?
No, I didn't see that.
Oh no, yeah, I cut it out because I didn't want you guys to be scared of something like that. Okay, I probably should now, considering you guys are just wanting to jump to the answer. Okay, so we have our phase constant, our amplitude, and now we need to figure out omega and our wave number, which is k. So luckily for us, we have an equation that relates both our wave number and our radial frequency, which is just k equals
Omega square root mu.
epsilon.
Okay.
Let's go back to our medium characteristics. I'll write them down here just so that we know what they are. They're at the very top that's given to us. So we'll say medium 1, and we'll just say epsilon 1 equals 5 epsilon naught.
How do we know that theta equals 0?
How do I know that this phase constant is equal to 0?
Yeah.
So I want cosine to equal 1.
Oh, because of the peak value.
We know it's maximum potential there, yeah, or it's maximum at t equals 0 and y equals 0.
What do you have plus 2 pi n?
So plus 2 pi n is because cosine also is equal to 1 at 2 pi n.
2 pi, yeah.
Yeah.
He's being too extra.
I know, you don't need to put,
Now it reverts back to A equaling to, oh my god.
you don't need to put that there, but
Yeah, you don't need.
technically you do, but whatever. It has to be mathematically
You don't
correct.
have to, but if you actually want credit.
You don't need.
He's not gonna take off points for that.
Oh, yeah,
The
you will.
exam is timed.
Exactly. So now we can just figure out what K and omega are.
Well, we can use 2 pi f because it says it's 6 gigahertz.
Exactly. So omega equals 2 pi f. F we know is 6 gigahertz. There you go. So omega equals 12 pi gigahertz. Funny number there. Doesn't really mean anything. 12 pi gigahertz. Okay. Now we can just plug in these guys, our medium characteristics right here. Let me just make sure this is an M and not a mu. This is a capital M. And then we have
the epsilon R, relative dielectric? 5.
5. Yep.
Oh, 5. I'm like, wait a minute.
So we have K equals 12 pi E9 times, okay, we can kind of break this out if you want to, mu naught epsilon naught times the square root of 5. Okay, and so K then equals 12 pi epsilon naught, or excuse me, E9, E9 divided by C times square root of 5.
Hey, what if what if you do mu when it equal to the relative, wouldn't it be the relative dielectric constant, so you would multiply both the...
It says what it's equal to as a constant.
Yeah, mu naught equals mu 0.
Exactly, yeah. So, sorry, mu 1 equals mu 0. Sorry.
That was given in the problem.
Yeah, it says right up here, mu 1 equals mu 0, which is kind of funny. There you go. So that's all I'm doing right now is I'm writing our medium characteristics.
So it's
What
just,
if you multiply mu 1 by mu naught?
Yeah.
yeah.
No. Mu 1 is mu naught. Mu 1 basically is the medium 1 permittivity. Is it permittivity of free space?
It's not timed.
Yeah, so it would have been square root
No.
of 5 times 1.
Yeah,
So
so
mu
mu
1,
one.
it would still be 5.
I will explain. Please let me explain.
He
So
would tell you. He would.
I will explain what I just did. So I will write it out. Mu naught, mu r, epsilon naught, epsilon r. Does that make sense to everyone?
Yeah, that's what they want.
Okay, so now what I will tell you is that this is mu 1 and this is epsilon 1. We know what mu 1 is. We know what epsilon 1 is. Mu 1 is basically mu naught, is exactly mu naught. Epsilon 1 is 5 times epsilon naught. Okay? And so this is now equal to mu naught 5 epsilon naught. Okay? And because I can just take out a square root, right? And I can just take out square root of 5. I can now rewrite it as mu naught epsilon naught times the square root of 5. And the only reason I do this is because it's easier for me to see that mu naught times epsilon naught raised to the 1/2 power is just 1 over the speed of light. Super simple.
Yeah, but that's not showing your work on the left.
It's okay.
-5 problem.
It's okay. Okay,
-5
I get it. I get that it's not showing work. Did I show that on here?
On the right, yeah.
I did, yeah. I showed my work on here, yeah. Okay, so on the right, yes, that's the correct work. Okay, now K is simply 4 pi times, actually just, I think it's 40 pi. Yeah, 40 pi times the square root of 5. Okay, that's your wave number, which is beta, if you want to think of it like that. Now we can write our instant electric field intensity as the following. So let's see here. Originally we had arbitrarily defined this with respect to x, y, z, and t, but we only know it's propagating in the y direction, so x and z do not need to be included. So we'll just define this as y, or arguments are y and t. So 10 volts per meter times cosine of our omega, which I will just say, well, I'll just write it as omega, who cares? We already know what, we already found it.
-5.
Control C.
Omega is defined there. Omega t Now, I will write this because I think he might want to see what we're writing.
Like, that's where I put my. Look at me.
Oh, look at you, so special there. Okay, and then we have no face constant, and
You have
congrats.
to divide that by C.
What happened to the X that had in the beginning?
Yeah, they have your
Excellent.
direction.
There you go.
Don't forget to divide the 40 pi square root of 5 by C.
We already did.
You sure?
Yes.
That's what it equals to after, because 12 divided by 3 is 4.
And then you have an
Yeah, you just did the-
E9 over
the
E8.
W over C and you just left out the pi.
I'm sorry, I guess
You're supposed to. It makes it a nice number.
C equals 3E8. Let's just agree with that.
Yeah, I see how you get that.
Meters per second.
That would be 2.99.
Where's the word for that?
Yeah, 1 over.
Don't you dare.
Oh my goodness, 1 over the. You guys are hilarious.
They're fine. Those are fine.
You guys are hilarious. Okay, let's move on, please. Okay. So, how many points did we get? I don't know actually, because it doesn't really define it right here. We think it's 40 points.
20 and 20.
We think it's 40 points,
The next part is extra
but
credit.
it's extra credit. I don't know how much he gave for this, so
The first part would have to be 40 if it's extra credit.
I would
We
hope.
know the 40 points is the extra credit on B.
Exactly.
The whole question.
So now for the part that I actually kind of like, I think everyone should like this as well too. We're dealing with medium or boundaries and instant waves on boundaries, right?
Yeah.
So let's figure out what we're dealing with here. So what I will define as our medium boundary is this point right here. So we'll define this as M1 and this is M2. Let's go scroll back up so you guys can get the characteristics for M2.
So more or less everything is the same except epsilon 2 is equal to 80 epsilon I.
Exactly, yep. Perfect.
Perfect.
And what does it ask us? It asks us to determine the reflected, transmitted, time harmonic
E-field.
E field. Okay,
Let's go.
let's go.
These should be similar to your homework.
This is exactly similar to your homeworks. Okay, so what I've drawn here is our instant wave, so I'll just define this as EI. Actually, let me clarify this for you guys. So,
You can use colors.
I guess, I hate colors. I can't.
Oh, sorry. That was.
So, let's figure out what, sorry, I got ahead of myself here. So, if we want to draw this out, because I love drawing, and drawing makes it problem much more simpler. So, I want to define a medium boundary. M boundary, and I want to define the top one as M1 and the bottom one as M2. So if I'm going to cross M1 to M2, I have to travel some direction, right? So I'm going to travel in this direction right here. Well, we know it's propagating in the positive Y direction. So we'll label this guy down here as positive Y. Okay. And we know that this guy is traveling, or excuse me, it's oscillating, so to speak, or its polarization is in the x-hat direction. So if we know that we are...
Could you move Y to the top and then M2 at the top and M1 bottom?
Seriously?
Okay, sure.
No.
I'm being okay.
I will move it to the top.
You
Yeah.
think spoiled.
Is positive,
You think
so.
spoiled is what you think.
I-
That's the second
I mean, it's
problem.
easier visually for me to see because it's propagating in the positive Y direction.
Drawing, and then you ruin his drawing.
We will,
We all know that up is positive.
we will define Y in that direction. You happy?
Yeah. Thank you.
Okay, and so we will now define this as M1 and M2.
I guess it's okay still. Like, yeah.
So we're propagating in the Y direction, we're oscillating in the X direction. So oscillating in the X direction, propagating in the Y direction, we're instant to this guy. And what are we also? We are also normal to the medium. It says normally instant right here. This is your big key phrase right here. EI is normal, which means that we're not at some angle like this, we're not at some angle like this, we're directly straight on. So this allows us to now draw our actual propagation wave as the following. Just horizontal lines, okay? And now I want to determine, okay, where's my other axis? Well, if Y is up, then X can be in this direction right here. And by up, I mean vertically on the page. There you go. And I will draw a little arrow right here just so that we don't get confused. This is just EI, E incident in medium 1. And I will kind of draw this guy as well too. This is your E transmitted. in medium 2. Sorry for the uneven lines. Am I okay to draw that right now, even though I don't know exactly the angle it's traveling? Of course, because we don't have any conduction, as well as, I mean, the reflected wave is going to be exactly instant, or exactly normal. Snell's law, right? Okay, your angle of incidence is equal to your angle reflected. If you're normal to the surface, then it's obviously going to be reflected right
Do we
back
have to
into
worry
it.
about any charge in between the crossover?
Oh, let's see here. I'm trying to think here, what would happen
I don't think there's conductivity.
if there's no conductivity, yeah, but I'm trying to think if your medium, let me think here. If you had a boundary condition where your medium was separated by a metal plate, let me take a look at that. Let's see here. A medium 1 dielectric, medium 2 conductor. You would probably have to do 2 separate mediums, or you would have to do 3 mediums. Your medium 1 would be your metal, and then you would do medium 1 to medium 2, or which would be your metal, and then medium 2 to medium 3, so that you can go back to whatever, dielectric or whatever. I don't think you'd be that crazy. If he is, God bless your souls.
We all know what happened last time.
Yeah, this is true.
The extra credit.
So
is
continuing
fine.
on, we will find our
Yeah, it's no longer.
our perpendicular gamma
One of the problems to solve.
60 points.
normal incidence, i.e. perpendicular.
Turn this into a capacitor.
Are you guys going to cover chapter 8?
No, we didn't get to it.
You didn't get to it? Okay, well,
If we
I
didn't
don't-
get to
I don't
it,
think-
it wasn't that much.
he might give you guys this as extra credit. That'd be funny.
That's not extra credit.
It's called
It's,
more work.
it's not counting against you.
What if we do the problem by memory on it?
So how do I find my intrinsic impedance of a medium?
Intrinsic impedance of a medium.
How do I find the intrinsic impedance of a medium?
125
That's,
times.
and not divided by square root epsilon r?
So yeah, so it'd be just, oh yeah, you're probably right. You probably just got rid of the mu naught because the mu because you don't need to really worry about it. Yeah, so it's basically just mu divided by epsilon, which is equal to n naught, your intrinsic impedance defined as 120 pi, multiplied by 1 over epsilon r, which is equal to 120 pi divided by the square root of 5. Okay, and now how do we find the second medium characteristic or intrinsic impedance? Same way. Excuse me. Mu over epsilon equals 1 over epsilon, which is equal to 100 over square root of 8. So now we can calculate our, this is not a y, this is a perpendicular. So this is gamma perpendicular.
It's kind of like it's a little.
Simply put, we can just plug in the values. So let's take out 120 from all these guys. We know they're the exact same, so we can just be left with 1 over the square root of 5, excuse me, 80.
It's kind of like,
minus 1 over the square root of 5. And then we have 1 over the square root of 80 plus 1 over the square root of 5. Hopefully you guys are proficient in square roots.
And he can write.
80 is obviously 20 times 5, which is made of, oh, excuse me, 20 times 4, which is made of 4 times 5. So you have 16 times 5, and then you have the square root of 16 is 4, so you have 4 over 4 times square root of 5. Okay, and then if you subtract it, you just get this guy right here, 3 over 4.
My work's so different.
Did you really do it differently? That would be hilarious.
Yeah, and I got the same answer. Look how much little work I did.
yeah.
Well,
just-
I think it's because we decided we don't need to show work. This is not our test. Okay, 4 over square root, 4 times square root of 5 cancels out top and bottom. We simply get minus 3 over 5. And then we can find our tau. reflected, which is just 1 plus gamma reflected, gamma perpendicular, which is just 2 over 5. Bien.
Bien.
Did you say earlier, this isn't our exam, we don't need to show our work?
I was talking about, we had looked at this paper previously and we were comparing our work and Monse was like, oh, I didn't do all that work, I did this. And it was just like, okay.
Oh.
So now we will just find our reflected and transmitted electric field intensity. So E reflected perpendicular, and we're not considering the parallel because obviously we're normal, so that that component is exactly 0. So we have reflected or gamma coefficient, whatever, in the perpendicular direction. Incident electric field. Okay, simply put, you just multiply. I'm going to leave this in the time domain right now. I think
EI?
ER.
EA.
But EI, yes, E instant, yeah.
Okay.
Which is in your medium 1. Okay. And let's think about something here first before I write everything
How
down.
do you even determine Hagman perpendicular?
So gamma perpendicular.
Yeah.
So, sorry, I've been writing this differently. This is not Y, this is
Oh my
perpendicular.
gosh, okay. That makes me-
I know that in some notation it's the perpendicular is at a right angle sometimes. So this is actually just perpendicular straight up. Here you go.
Is it also tau perpendicular?
It is tau perpendicular, yeah. I'm sorry for confusing you guys like that. There you go. And this is also 1 over gamma, or just gamma upside down t. Okay, now we just got to find our reflected from our
What's that
incident.
symbol supposed to be? It's a gamma perpendicular, the last line.
This one right here?
No, the next one.
Yeah,
On the
next to
right.
that thing.
Oh.
No, the,
No.
the other one.
On the right. You said on the right.
In the middle of those two that you just.
It's just E, right?
That is E.
Instant.
Oh,
Yeah.
God.
Is that an E?
Yeah, that's an E. I have
I asked about that earlier.
E. There you go. E incident.
E is
E
electric
sport.
field.
E A.
Electric field
It's in the game.
intensity.
Yeah.
Okay, so we will now write down whatever this is.
It looked like a 2 in a box.
We will
Some like weird symbol.
we will multiply this by 3 over 5 cos of omega t minus ky, or plus ky. Oh shit. Okay. Let's leave it as minus ky.
Cool.
Is anything wrong with this besides the missing x hat direction?
Yeah.
Well, it's
There's a lot.
propagating in the positive y direction, which means it would be K.
If it reflects
negative
back,
K.
should it be positive?
Correct. It reflects. So this guy right here has to be positive.
Does all of it reflect back?
All of it reflects back. This
This
is
is the reflected,
this is excuse me.
It goes to the y
Mhm,
direction.
I see why.
It goes in the negative y direction. So if we look at this guy right here, we have our y hat direction, which is pointing up, which is what our incident energy was traveling in, or sorry, whatever incident E field was traveling in. Now we have a reflected component that's exactly, parallel to whatever our incident energy was, incident E field. So now it's going in the minus y direction. So that's why I asked, okay, is there anything wrong? Yes, this guy right here has to show the direction. So it has to show minus y direction. And so I knew when I was going to write it down as minus ky, that was wrong.
So R at the top means reflective.
Correct, yep, exactly, reflect. I think that's how your book notation has it as well, I hope.
I mean,
That should be, it's simple to remember, reflected, incident, and transmitted T. Okay. Now, obviously, this isn't the right answer, so if we want to get this in phasor form, then we just do, we just do R. Do we have x hat in phasor form? I think so, yeah, of course we do.
Yeah.
e to the jky. Okay, there's that one done. There's your reflected, and now we do transmitted. T perpendicular. No parallel component to the median boundary, so we don't have to worry about that. What direction is this field propagating in?
Sorry?
The
What
Y?
what direction is our transmitted
Oh, wait, no.
field propagating in? That's the no propagation. Correct, the y direction. It's going through the boundary. Doesn't change its direction.
No, he's asking why you asked that question, but
No,
got
of
it
course
right.
not. He's not.
I'm kidding.
That's a great one. That's actually pretty good. I didn't think about that. Yeah, exactly. It's the same direction as the instance, so no worries about what we're doing here.
What's the unit of power? What?
Watts? What? You do that to what?
Wait, why are you writing ET perpendicular? Is like, wouldn't it be parallel? It's tangent, so,
Perpendicular to the boundary.
oh.
I think in the book, they just leave it as nothing, because they talk about perpendicular polarization and like parallel,
Yeah.
and they use those for another set of equations.
Screw him. This is it keeps
Watching, come on.
it keeps. I mean, it obviously keeps your like mindset on like what you're looking at. I couldn't tell you what ET without anything was underneath it. God help you if you can. Times 10, x hats, cos. I'm only writing the time domain version minus ky because it's in the same direction. Okay, then we do 20 over 5, x hats, e to the minus jky equals our transmitted one right here. Transmission coefficient, I think that's what it is.
So there should be one of this part, right? Or is that?
And that's it. That was literally it.
So it's just transmission and reflection.
Exactly.
Wow, that was so easy, guys.
40 points.
Oh, wow, a lot of hope was.
Wait, can you go back to the bottom part? I think I read the reflected wrong.
Did we have to write the wavelength and?
No, not at all.
You didn't ask for that.
Why did I get voted like this?
Don't ask, don't tell.
Kids in middle of them ask them, put this on the test.
Make sure everyone else feels that.
I
you
think
get more
because we
points,
didn't
therefore a higher-
time vary. It's time. This is time varying. That's not time harmonic, which means time is not considered.
And then this
Or
last
time
one
is
they
out of
all
there. It's
right
assumed that it's somewhere. But
I feel like you're
Okay.
Christmas retake.
Okay.
Oh, I would love to.
there is another video up that basically covers the first two problems that we did. They are different. Let me see how different they are. So the first problem that we cover is also quasi-static approximation. It asks you to find the electric field intensity, time varying, asks you to find the self-inductance of the coil, and then asks you to determine the time average power in the resistor. And then the next problem after that is just the first problem that we did essentially, except you have 377 times some polarization times some exponential. And so when you see 377, think to yourself, okay, well, I will choose my intrinsic impedance to be 377 instead of 125. Just make it easier for yourself. Ask you to find the time varying or time harmonic magnetic field intensity, polarization state, frequency, and time average power density. Does everyone know how to find time average power density of EM wave?
Yeah. Half of the real part of the electric field times the conjugate of the magnetic field.
Cross product.
Cross
It's
product,
the
yeah.
cross product, exactly, yep. S is equal to 1/2, is there gradient somewhere? No. E cross H. Is there a mu naught? Yep, okay.
Okay, I finally learned right-hand rule while you were doing that problem.
Awesome. And then this guy's in watts per meter squared, sorry. This is not the
real part, right?
It is the real part, but yeah, so SAV average is equal to, oh shoot, hold on, let me rewrite this, it's not half there. 1/2 here, real of S, your pointing vector, watts per meter squared.
What is this?
S is your pointing vector,
Oh,
or your time average part estimate.
Right on the money.
And then there was another one that we just covered, so. Awesome.
oh yeah.
Yes, there's lots of ways to solve for that. I'd always do the cross product. Don't take any shortcuts, please.
Just do it.
No problem.
You could do through my left. Okay.
Okay, any questions?
Any questions? Todos preguntas.
Preguntas?
Preguntas clase.
All right, thank you for the help and the review. Let's get a big clap.
I do.
All right, just me. That's cool.
All right.
Yeah.
Gracias. Thank you guys so much. Sorry for keeping you later. You guys, well, actually, you guys made that decision, so it's your fault.
Well, you know us, engineers.
Here all night putting magnified fluid.
When is your test?
December 7th.
December 7th. Wow, you have time.
Oh, yeah.
Yeah, so they have time to
Time
bug us
to
over the
kill.
weekend. I'm just kidding.
Okay. Are
Let's
you,
go
where
work on
did you
that
record
project.
that?
Oh,